application that you all have seen. Either you can, if you wish, how many of you did not see the application on rice grading?
Actually, Professor Vrinda Verma, he has shown certain slides.
Okay.
Out of rice.
Okay, so they have application wise they have the idea. Okay, so I can, many of you have visited. So I will just take the application now, how it was treated from very first process level to the last level, because it involves neural networks training and a lot of other things also. So I was just trying to know how much time we can have. So these are of course the overall applications. Now we will categorize into, as you have seen now, many of the applications are real time. As you saw, apples or potatoes or eggs or anything. And some of them, the application that you will see now is low speed. Basically, it's a laboratory kind of analysis that we do for rice grading. So these are basically the three categories, not just meant for agro processing. This is all for, you will find it's like low, medium, high kind of speed wise. It is towards speed, the kind of applications you will require. So medical applications and agro medical applications or any lab applications. Report-based applications would be low speed, or in fact zero speed you can say, where whole in-depth analysis is done. That's the reason the applications that I have chosen will require, will give you in-depth kind of understanding. Because when there is a motion and other high-speed requirement, then they place speed as prime issue. In fact, for Apple applications that I have not discussed, they don't go to the details of what we have gone for rice applications. There we are using neural networks and complete intelligence training has been used, which is not possible when you run with high speed requirement. So medical and agro applications or any lab diagnostic applications can afford to be very intelligent, at least as far as the present architectures of processing is concerned. With the architectures improving and processing going faster, you can imagine more intelligence going into the machines. At the moment, machines are going for speed. Their purpose is to get speed at some low intelligence also. So their main throughput is through speed. So with this, the three categories. Next. Okay, this is just again I told you, depending upon the processor speed, you can choose the processor. Next. Okay, this also you must have covered through processing wise, the low level processing, the medium level processing and the high level processing. Now all these levels we would have in the application that we have. The pre-processing will give you image processing. The true image processing that the whole course is about is the low level image processing. And it may go at the max to medium level, wherein you transform the image to another domain. But this the project that I am now going to show will give you even the highest level, that is matching and classification. So if you do the final thing wherein you can make decisions, that is the high level processing. Wherein it is not actually the image level processing, but the extraction of features, the extraction of data, the data reduction that you have done from the basic pixel levels to the higher level, scoring and grades, that gives high level classification. That is basically statistical or other methods of pattern classification. So basically you will find the image processing as such remains low level, where image generates another image. Or medium level, where it gets segmented, but it should transform. When it transforms, then only it is medium level. If you are still seeing the image, that means it is still at low level. So there are three levels to reach the ultimate application. So most of the image processing applications will maybe at low level. Okay. So segmentation, as I said, breaks the image into the areas of interest, and that's where the image is divided into smaller images. But that time we can say it's the beginning of medium level. So that with that kind of classification of the levels in mind, we go ahead for the projects that we discussed. Next. Okay, that's the application some of you had a chance to see, and now you will have some detailed treatment. I would see that if you feel appropriate, many of you have seen, if you can raise the queries in between, it will be better. Next. So I can sometimes skip certain things or provide. The idea is that for this application, I have given everything here, but as for the time available, we can see the discussion limited to what is of your interest. So this is from the national requirements of rice grading in the country. This is related to this very our own country requirement. But the general term used is fair average quality. That means fair average quality is the kind of acceptable limits. It's like pass marks, you can say, kind of thing. And under relaxed specification, these are the terms they use. Relaxed specification means, okay, it's like you can do 5 out of 8 questions. You need not do all the 8 questions. Similar to that, we have relaxed means there is a percentages of refractions allowed. That you can have some broken, you can have some damage, you can have some white chalky grains. You will find some defects list I will give. That means there are percentages allowed. That is the relaxation.
Yes, available machines for sorting out the rice.
No, not to the 10 refractions that we have seen. There are rice sorters are there. They do not follow the standard that you see. You can control some of the features. Some of this is after the milling and sorting is done.
I came to know that Market has acquired one machine which they use for the sorting of the rice.
Yes, sorting machines are there. What do they do basically? They use RGB similar cameras that we said for apple sorting. That after the sorting is done, this will give you acceptance on the lab level. The sorting doesn't follow all those things. They will say you have to set certain parameters. The speed is the prime issue. If they know they say forget about damage, you can't see the damage. So all the 10 classifications are not possible with the sorting machine because the speed is prime. I told you they cannot manage. They just do color RGB or any conversion. Generally, I am told that for Apple also they are not able to go beyond RGB.
Even size of the rice also.
Size
of the rice.
Size is possible. Geometry is generally easier because color is a problem. They do colorful color also in the sorting machine. They have Sortex machine. Sortex. So if you see, they put the rice grains are falling at a 40 degree, 45 degree machine. It's like a ram falling. During the falling, there are scanning cameras. There are two or three cameras, in fact, similar to RGB. They put 3 diodes basically, and based on that, the motion gives the length. I mean, they do manage acceptable kind of lot conversion. But when it comes to milling and then humidity, the discoloring occurs. Now they have already stored, sorting has been done, or discoloring has occurred. After storage, in between the humidity effects are continuing. Chalkiness is changing. So there are few things which they require at the time of procurement. The sorting has been done, the packaging has been done. This is an additional step they do manually. This is a manual step. This is not a sorting. It's not a replacement for the sorting. It's a second level when you procure a sample wise. This is a sample wise grade. Like you show us a sample now. You're buying it. It's a buying or selling situation. So during storage, the quality is changed. Particularly the discoloring occurs, and any failures that have normal grain, they say to go for always when they procure, they have a manual kind of testing. Half an hour testing is it.
Pepsi is using to see the size of the potato. They are using some kind of.
Yes, I told you potato manufacturers are asking the CPRI Kasoli, who is having collaboration with us, for the right time to exit from the storage. They want to have a reverse calculation, see that right state of the potato, so that the chips formation is in good color. If it is not in good, if the potato chips finally made is not in yellow or appropriate shade, but is browning and other shade or greening or any other color, you will not, it will not last in the shelf at the house level. So this is a linked process. It's not ending at one place. What I am trying to say, it's a living object. If potato is not a shell product or any rice or anything, it's a living kind of thing. Every moment it is changing. It's not an engineering product that if you inspect it once, you pack it, seal it, 1 year it can stay as it is. They are changing. So if they are stored, they will change. Humidity is changing, temperature is changing every moment. What are the storage conditions? So we have we are running 24-hour storage, we have developed some storage area, wherein lot of instrumentation and monitoring and control is going on. And if you do a problem, if one temperature sensor has gone bad, or the gas extraction has gone bad, then the whole product lot is gone and the profit is achieved. What I am trying to say, in between the profit is achieved. The agro products or the real life products are changing. We are aging every moment. If I have a medical chapter, I have to have it again tomorrow or next month or anytime. So basically these are lab testing at a second level after the sorting is done. Sorting and milling, this is a milling process also involved, wherein the peel of the rice grain is removed. The particular humidity level removes the peel. That gives you white grain that you see, isn't it? So that, and if you have more humidity in it, then it will have a lot of breakage. So this is, if I show you next, you see that these are the overall, what are the problems with it. The good ones are here, and there are 9 other classes. So it's 1 plus 9. It's like Ravan with 10 faces, you can say, only one is good one. So the sound one is this sound, and all others are not desired. So, and you see the sorting doesn't guarantee 100%. Even this will give you also sample report. While sorting machine sees every grain one by one, but doesn't see the whole thing, and may miss certain percentages of say red, this color or whatever, and this one sees a small sample. See the problem with both the machines. The sorting machine sees every grain but doesn't see the whole thing. This one attempts to see the whole grain but doesn't see the whole sample. It sees only 20 gram as some of you observed. This is a very small sample lab level testing done that, okay, have a 20, but it is drawn through statistical sampling from a larger, say larger base of the whole storage. So considering this as a problem, the market only has given this problem. So they have an equivalent, they were trying to procure a lab equipment for that, which is different than sorting. So sorting machine is at a field level and this is at a lab level. So as per the standard, now this of course is size based. This part, big broken, small broken, organic is also grain in the near 1/8 size of the grain. It's like a powder rice grain, very small. So sound is the full grain, and people have to do it by about half an hour for 20 grams. And they do, they sample each and then weigh them separately. That okay, out of the whole 20 gram, how much percentage by weight was red? How much percentage by weight was all these? This is chalky, this is the lightest of all. Chalky, damage and all that. This is the starting point of the problem given to us, say. With this only as acceptable and all others not acceptable. Inorganic means unedible material which might have been encrypted inside. So with that next and starting point, next, of course this you have seen how the imaging is done. We have thought of this as method for acquiring the images as static. And next, particularly we found that the RGB quality, color imaging quality of the scanner is much superior to any other camera, as I mentioned, because there are no lighting variations. It's a complete, any other camera based will require at a distance. When you see the object at a distance, the illumination problems are increasing. And lighting variations create the imaging defects. So imaging variations. So therefore, people have also used this in the literature. At one place I have seen, they have not used it for color, they have used it for geometry, for detecting broken, full broken and small broken kind of things. So that is the idea as far as the usage of similar thing in the literature is concerned. Or otherwise typically you would require again, as I said, 3 CCD, minimum 3 CCD, and this scanner of course gives much rich quality of the photographs if they are flat, of course. This doesn't do for Apple or anything else. This cannot work for any object. Even for grains, because they are very small in size, so we can afford to see a more major portion of the grain. If again we miss part of the grain, that will be a limitation of our work also. Okay, next. Okay, so I will give you next, I will rather give you steps by way of visualization. So, most of you have seen that you throw sample on the flat bed scanner and the pre-processing is done. So that basically, if you see, the image processing is done at this level first, that is the low level processing is only this much, which gives you some smoothing operation. Have you gone across histogram analysis? Some smoothing segmentation by on this course, some discussion. So some filtering you have done?
Filtering, I definitely.
So the smoothing filtering is the low pass kind of filtering, which allows us to make decision for threshold detection. So I will show you how it is done, but at the moment it is only step where we try to get a black and white kind of image for size detection. So the first level is smoothing only on red. At the moment there is no HSI conversion, only red filter, red band of the split RGB images. Then comes, after we get the geometry or I think I will rather show it and then come back to it because it will be easier to see. Next, we will show that next. I will rather show it first visually so that you get the idea of what is being done, then we may come back to the diagram for summarizing. This shows how the image sample is obtained on the image from the scanner. Next. This is the analysis that I think you must have done this. So this shows the histogram, wherein histogram means it is showing all shades of the image as statistical sample. On left hand side, on the x-axis we have intensity. If you see 0 to 255 as the intensity, and vertically y-axis show the population as to how many of them are in particular shade. So it's like a class histogram, you can say. It may be like these many students are, or these many grades are having the intensity from, say, certain value here, maybe 30 to 50, which is a darker domain. Actually, this is not grain, I believe. This is a whole background, black background. This whole area is showing the background. And here is the rice heap. All rice grains are in this domain. It's like all pass ones and these are, say, black fail ones. Not fail ones in background. This is the basically grain area, which all the grains may be grain in shades of, say, 100 to 150 kind of gray shade. That is the brightness level each grain is exhibiting. All the 10 grain defects are also in the same area. So what we do is first to segment it. The segmentation step means you try to extract it from the background. Again, I will show you next when you understand what is the meaning. Next, this is what we mean by segmentation. Segmentation means now there is no color, it's only binary, it's only black and white, but it's like drawing now, it's a drawing. How do you do mechanical machine drawing? You have an object, you make a drawing. It has no color, no shade at that moment, but you can make measurements. So same way when it is black and white, we can make measurements. Measurements in the sense we can make geometrical parameters extraction. So we are able to make length, width, perimeter, area, and many other. You will see the list as the geometrical parameter. So this is the step for geometrical extraction of the features. So we are going from low to medium level processing. So the next one. So this you see as if the whole set of grains has been put on the drawing board. That is the reverse engineering. What I am trying to say, we do all reverse engineering in case of agro and medical applications. While industrial objects will have, you have models. You have designed a table, you have designed a pen, a laser pointer, or anything, you have designed it. You have conceived it in your mind, you have conceived it in your CAD, you have made a shape to it, then you have processed it and shaped it. When you do image processing, you have to take it, but you know how to model it. When you inspect a product of this kind, you already know what is the geometry of this particular product. You can match it and compare it. But for this kind of object, which is a real object, you don't know, you have some basic idea from the rice experts, but you don't have actually produced it by drying. So at this moment, it is ready for you for kind of feature extraction. So that the way it is seen, the orientation has been detected, the length has been detected, the width has been detected, and a box has been fit as a room has been given to it, wherein each grain has been indexed and labeled. So each grain is numbered here to show that the extraction gives full segmentation. Now mind you, this showpiece, I would say, has been obtained by the previous image that we just saw. That means we have done all the size and indexing judgments on the black and white image that you saw. This is only superimposing thing. It's like I have got your number, roll number, I have pasted everybody's roll number on his face or maybe on the chest, or it's like carrying a chest bag number. The processing is not been done on the color or grain image at all at the moment. This step is based on the only binary image processing. So this step, that's why I just want to show you. And although they appear gray grains, but the imaging that is going now behind is color. That means all the three colors are used now, are in fact now going to be used. Till now we have not used the color. We are now going to use it by labeling it in this manner. Next. Now see, another step which many of you had observed during the demonstration there, that once the grains are spread over the scanner, they may be touching each other. So segmentation did require, it's like very close friends, very close by sitting. So you want to count and identify them with a slight demarcation line. You see the demarcation now. Next, you just press next, you will find that. See, it's like very close ones, they were touching nearly, so there is a segmentation done. Particularly the segmentation is very nicely visible on certain cases here, wherein there is a line generated here, and it could not be generated here. It could be generated wrongly at this place, and this is, some of you might be interested in research. So water shedding and segmentation are very important areas, wherein I would say the problem is never at a successful or a complete perfect level. So many of these situations here show the segmentation by way of water shedding, wherein we try to segment the objects who are very close to each other. So next, yeah, next, you press it. This shows, of course, which I just showed you earlier, that each grain after binarization, after water shedding, that means all geometrical size parameters and indexing and labeling. Now this is the labeling generates, this is done only by monochrome or non-color based image processing. So this shows now you can see some of the boxes are overlapping also. So there is no problem as such as far as overlapping is concerned. As long as now these two have been coupled as one. This will generate wrong result. This grain will appear as a new object, which is a longer than, it's like an object of this kind. We will have to remove it from the analysis later on, but at the moment it has got into the index. It's like detained, to be detained. It's that situation, but most of them have been sorted out as the success of this step, I would say, is 95%. Even this step has its own success. Water shedding or segmentation may not be 100%. So many times when you analyze reports and research papers, every step has a success rate. And therefore anybody claiming the result at a later stage would have not or might have not covered these results. So this is what I am trying to say. So as far as this, now onwards will be the color processing. Next. Now, if you go back now to the diagram, this is now giving you what we are doing as far as the overall feature extraction is concerned. So we have reached this level basically. Now we have also got the labeling, numbering, indexing done. It's like roll number indexing has been done. Now the images are split. Dr. You told them probably as split RGB. At this moment, we have got each grain available on the image platform where it is, and even segmented from its neighbor. Then we take all their RGB components. And RGB components of each grain independently are taken, and their labeling has already been done to to get the color features. Now, what are the color features? First, let me just keep a binary image with these parameters. I don't know whether you get, some of them are easier to comprehend, some of them are derived from the geometric parameters. Like, for example, elongation is ratio of length and width. So basically they are length, breadth, area, perimeter and convex perimeter only. Basically these are the geometric parameters. The others are derived from that. For example, roughness is derived from convex perimeter ratio divided by the actual perimeter. I don't know whether you covered some features. So basically, it's like a table here they have actual perimeter and other perimeter will be using a thread. I go to one corner, straight go 4 corner and that's the approximate perimeter. It doesn't take care of this shape part, actual shape. So that ratio gives me the roughness. So that is where the, as similarly rise also is measured in that. So there is a lot of detail about the feature extraction. And similarly, how this is done, this could be of interest as far as color image processing is concerned. Wherein we gave classification, color defects are sorted as sound, chalky. Basically, these are the color defects. So there are 10 defects, but these are the color defects, that is sound, chalky. Now, how do we do it? This is where the experience and domain came. Market sampled a large number of grains and gave us labeled list. Now their labeling was, here is a grain which is red, here is a grain which is chalky, here is a grain which is this color. Now I am looking at it, I don't know whether what is its RGB, what is its HCl, I don't know anything about that. And also the red grain is red at different places. I mean it is red at some place but all other else is fine. It's like a criminal saying, you know, someone in Plaza is a terrorist. Looking at his face, it doesn't look like a terrorist. You know, it's what I'm trying to say. What do I see in that? You know, it's like this. Somebody says this is a red one. You say, how do you say red one? No, see, there is a red. The whole grain is fine. There is a small spot. So that gives it a defective red. It classifies it as red. So I have to take that, okay, somewhere it should have red and some smaller percentage or a particular, it's like a person who has made one theft, one robbery. So it is a robber. Like that, sound one, okay, sound grains are whole sound. The good ones are grains without any defect. Chalky ones are also chalky more or less because they are in white color. But defective ones, for example, red and damaged because it is slightly damaged here. So what I am trying to say, the defects are very local. As you saw defects on the egg, a small scratch on the apple or fruit, anything makes the whole thing as dead or bad. So that's why inspection of defects on the surface is a very small percentage of the area that you have to focus. And looking at the whole you may not know, and we have a skipping of that. So what we did, how did we train the system? We took those samples and each pixel was considered, okay, this is the red mark. Say in this case there is a pink. So we classified, if this appears, I will call it red. If we had a good sound number of samples, we analyzed them, okay, this color appears, this is a sound color. It's like a fair skin color, we had a sample of say fair skin and you have that color model HSI as fair. So like that, what we did was that each pixel was first classified as not green. First each, it's like considering a person as fair means every spot of the skin first say this is fair, this is fair, this is fair, each point on the skin is fair or not. If all 100% is fair, then we call fair. Or 90% fair but one mole is also fair. These are the rules kind of things that we make. So first classification was on the pixel level, then on the whole level. Next, if you see the rule base here on left hand side and a training based system was the whole system. Next, now we can come to the rules and then that will summarize it. I think it's already getting late. We started at next class. I think next. Yeah, this is also required because as I said, the weight, because the report has to be given weight wise. So we also trained the system for, basically we knew their weights, they had given us grains, this was the lot they had given us. So we used them and as I said some of them are very small in number, as small as red grains are only 14, isn't it? And we had a mixture of other grains. So we could find their density also in terms of gram versus area. So that the whole report could be given as weight. Next. So this is of course the rule used for which I just mentioned. How do we say? Now it's a range. If H is in the range of 7 to 25 degree, S in the range of say 0.2 to 0.45, and intensity in the range say 60 to 90%, we are calling each pixel in the range. Now whether if you like it or not, you may suggest, or anybody may find this is too bad a rule probably, but that's the way the range of rule is, to call it a red. And if it is this range, then we call it discolor. Then this is only as far as pixel is concerned. That means we consider all pixels are red with this band of features, as far as HSI features are concerned. And then the chalky, for example, a particular pixel is chalky if it is a large range. See the large range, 13 to 120 degrees of hue, and 0 to say 0.26 degrees. This is by way of who gave us this table actually? No one gave us. This we have to resort ourselves. Because they give us only samples. They don't know what is HSI, what is RGB. Say, here is the grain. A person can easily understand. Why can't you understand? It is as simple. The domain expert will come to you. Here is the cancerous tissue. Why can't you understand? You make a system out of it. And it will take ages for you to understand what he has understood in 6 years. See, if a human, after generations of evolution from animal to monkey to human intelligence has taken years and billions of years, and now experience of 10 years makes him understand cancer. You want a software to understand in 2 minutes. So that's where the problem comes in. So this is what we try to do it by statistical analysis, and then next a set of rules will give you. This gives you basically then as the, if length is say between 3.2 to 6 and breadth is between this more than this, and see the crosses, you forget. Because this student has scored 80% marks in 80 in physics and 60 in chemistry, we select. Forget what he has done in English, Hindi, math and any other thing. Forget all crosses. We are ignored. We call it something say admixture. And then that's what we do in a rule that humans form. You cannot form a rule. I call a good friend because he has invited me on his party. I have invited, he has attended. There is no set of rules that you can call what a good friend is, or anything for that matter is. You cannot form rules with more than 2 parameters. So rule-based systems finally at a higher level also collapse, and maybe then fuzzy rules and all this can be used. So we had all these rules, but we were using only 2 or 3. See, at a time we tried, say discolor means it should be discolor of pixels should be more than 2.7% and damage should be less than this. We tried to do this, but I am trying to show this is called range analysis. It's like who suggested you that 40% should be a pass marks? Who gave that figure? Why not 50, 70, 60 or? That means there was some merit, some judgments from the field taking this can be considered pass. All that statistical analysis has been done by experienced people, and that's how we try to do that. And anyway, look at the results, then you will find that this kind of rule-based system does not produce very high results, and then we sorted it to try to do neural network training, which considerably improved the results. Next, just see the, I think this, maybe next you can see the graph, it will be easier. Next, okay. Now this shows the using the rule base. Somewhere we got say, if the numbers are good, if the statistical samples are high in number with us, we get some 90%, 80 to 85 to 90% kind of results for certain things like green here and chalky is here, and then sound is here, and then for most 4 to 5 classes, which are larger in number. And when it is red, I don't know, somehow red also was reasonably okay here, because we were more concerned into where is the red, because this is very serious to be checked. Maybe for our own close observation, the rules could be found reasonably, still the results were not higher than this. Next, this is about more than 5,000 kind of thing. Now these details are using neural network, so this shows the basically validation where training gives this result 71%, 97%. The diagonal, if you can see, gives result for the classification, while training, while this is actual testing. So basically the training in the neural networks, we had a neural network training also done on the same data that we had obtained from previous processes, and then the results are obtained here. What I am trying to tell you here is, you may have an inorganic trained as 100% and the result performance in the field is only 8%. Because the training was poor. The number was very little. It's like good in the exams, good in the class, bad in the field, placement. So the training, this is a sort of placement, production as they call it. Production model means the neural network is used for unknown data. The testing is done on the unknown samples.
So you said you trained for 5,000?
5,000 in between 80-20. Yeah, 80%. Yeah, of course, yeah, 80-20 rule. Because in between there are classes which have only small number of samples. See, basically,
more number of
we need more number of samples. We need to train it. Yeah, it requires a training. And that's the logistic conclusion we got. That we had good results on sound finally and choppy, the basic qualities, wherein the problems are. But then there are defective ones, we needed more. Then we asked them, give us only the defective ones. And that's where they had difficulty. They say, oh, we don't have, we throw them away. We said, don't give us sound samples, you have got enough of them. Give us 2,000 red grains. It's like, give me 200 or someone that I can find out how to find it. Isn't it? There's a no, there's only one. And that is also hidden. So where do you train the system? Somebody say you should do the, we had a power plant system here, Hopper. You wanted to train a neural system to see the failure of power plant. Do you wait for failure to occur to have a data for that? Or you keep recording things and let the things fail? So what I'm trying to say, the experience comes at a high cost. So if you don't have data, even nobody can do anything. It's like our earthquake prediction. How can we predict earthquakes because we have not seen them? So similarly, the training required, if you want to detect the most, what is not at all compatible with you, isn't it? You don't find that it's not that they have no grains, but what I am trying to say, they generally get effects in small number. So the largest number was in terms of sound, choppy, the major grains broken and found. Next. So I think that is what will be. This is just showing you the results there, neural network training. This was using only the small number of features that we used. Another improved was even better than this. This was matching the rule based wherein minimum number of features were used. So therein you could find most of them, only few like inorganic. See 100%, when you train it shows 100%, when you test you find 10%. So these are not desirable, that means the training is not yet good. But for most of the other ones, wherein we had good number of samples, the neural net training was a successful kind of thing, wherein the training and validation was nearly. So it's a lot of statistical pattern recognition and probability theory that comes in. Larger number of experience you have, samples you have, the best training you can do with neural net. And the problem is well resolvable. There is no problem as such as far as resolving the classes is concerned. The only thing is system should be trained. If a child has not seen number 7, he has seen 1 to 10 and 7 is never shown. You say what is this number? You say, I don't know what this number is. Isn't it? So he has to see all the numbers. Similarly, the neural net also had to see all of them in equal numbers. If you show same thing and again, the neural net training also is higher on the particular side. And that was evident. See here, sound ones are nearly 100% now. Training or testing, no matter you do, at least it can find the sound one perfectly. In comparison to all the tests, it will have very close percentage, 98 or 99, 90. Very small. Similarly for other classes also, except for 2 or 3 classes where the number was. Next. So I think that for fine when you use all the attributes we had even better. Next. They were even, now most of them were close except this one, 1, 2, 3, 4, 5. Even 5 classes were still not into the acceptable, with very few exceptions are in urban areas. When you use all the 39. That means this system also requires even further improvement, is what I am trying to say. we must require at least 5,000 of 10 grain, 10 varieties, that is 50,000 grain training is required, I would say. Then only the system will perfectly work. Next. I think that's all about the comparison, and I think next we can have conclusions of it. It's also showing how the histogram, I think I will stop here. It is showing the how the whole sample, because they can see the process. If somewhere length is going 10 mm, this is that grain which was bad in water settings. That means two grains were joined together and the length was showing 10 mm. Things like that. Next, so I can leave it here, I think, for training my. This shows some of the points one can read. Basically, there is a lot of social involvement for this, because a lot of buying, a lot of selling, not only social, there is a lot of political problem also with this. Many of the people who have come to us for promise to give us samples are disappearing. And many of these chief of markets said this system can remove the corruption in the system. So there are a lot of vested interests which are also on the way for implementation, training and all those things. Because they say whatever be the system, at times we have to procure at blindly, whatever it is. They allow a lot of human moisture and other failures, then they have to have political pressures. Otherwise, the rules and everything is very finely specified, that this much of percentage of moisture, this much of all the defections should be allowed and not allowed. Basically, I was trying to give you only the social impact here, wherein you can have naturally good quality of grain, even from the ration or any normal rice procurement, provided the methods, the statistical standards that have been set are followed. And many times I have been told that they are not followed. And that's the reason they don't use the instrumentation. They rarely use, only in case of conflict when it happens. Then they, well, I leave those things away. I can only say that we are trying to now make it online so that the sample could be tested by anybody in the field by using the internet and our server. So the idea should be online testing. That is the addition we are doing it. So thank you for a long, patient hearing before the lunch break. And any points